Okay, this is chapter 5, number 31. We've got two boxes, one on top of the other. They've got cables going to the left. There's the pulley on the left. And first one, I made the list of all the givens. Mass, the first mass 3 kilograms, second mass 5 kilograms. When it's static, when it's not moving, then the friction is 0.6 between all surfaces. When it is moving, it's 0.4 between all surfaces. So here's a free body diagram. It shows the force of gravity, the normal force, the tension. There's also friction. It is being pulled in this direction. So if this is the direction of motion, I'm going to make that the positive direction. So since it's moving in that direction, the friction is in the opposite direction. I'm going to show that right here at the point of friction. So here I'll call it friction. Friction of box 1. I'll label it that. Now here for this one we have again force of gravity acting on the second box, a normal force. There's the applied force that's making it go in the first place. So it's got a tension force. It's being pulled back, resisting, being pulled forward. So the acceleration is to the right. So that's, in this case, the right is the positive direction. The positive direction represents the direction of motion. Here is to the left, here's to the right. Okay. So it experiences friction between the table. If it's moving to the right, it's going to experience friction between the table and itself. So I'm going to call that friction force of the table. T for table. FRT. Does not stand for frat. Okay. There is also the friction force between the box, the little box and the big box. So the question is, well, what's the direction that the force is? Remember that in this case, this is Newton's third law. This is for every action there's an equal and opposite reaction. So the friction force of that box 1 is really box 2 applies to box 1. The reaction force here is that box 1 applies to box 2. So it's equal and opposite. So it faces this way. So that's the force of friction applied by box 1. I'm going to keep it the same notation just to indicate that it's the same magnitude. Maybe not the best thing. Usually you write down 2 and then an arrow to 1, so the friction force of box 2 applying to 1. And here it's 1 with the small arrow to 2. But this is a complicated one, so I'm just going to show that it's the same magnitude that way. Okay. Let's do the some of the forces. For box 1, some of the forces, let's show it so we can see what it looks like. In the x direction equals, well, it's the positive direction is the tension force minus the force of friction. Okay, and it's okay. So here's the thing: it's asking what will get it moving, what will start it moving. So it's not moving. We call it 0 because by applying it to 0, we know the minimum value needed. Okay. Box 2. Sum of the forces in the x direction equals, this time it's the applied force that's in the positive direction minus the tension minus the friction force of box 1 and minus the friction force that is applied by the table. So that equals 0. It's not moving yet. We want to get it to move, but it's not moving yet. So we started at 0. That will tell us the minimum amount of force needed to get it to move. Let's add this up.